Okay, so we looked at some modern observations and I talked a little bit about data and some platforms, coverage, time resolutions, etc. But whenever we are trying to understand where the climate is going into the future as we keep adding greenhouse gases, or even without that, you would want to know how climate may change in the future. For that, you need to have a very good sense of how it has behaved in the past. There is a concept called climate sensitivity. So when we change greenhouse gases like carbon dioxide, how does Earth's climate respond? And with all the internal feedbacks that we already kind of mentioned, with humidity, CO2, glacier melting, albedo changing, etc., we want to know what are the range of possibilities that exist in the system. So paleoclimate is the study of past climates, and how can we do that? We basically need to collect evidences for past climate variability and climate change, keeping in mind again that there is no strict definition of how long the climate has to go away from what is now to be called climate change. But generally, if you think human timescales of a century is a good measure of climate change. So there are various ways in which past climates can be reconstructed using chemistry. Fantastically amazing advances have been made in using chemistry to infer past temperatures and other things like carbon dioxide, etc., location of the continents, plate tectonics, volcanic activities, and so on. And we call them inferences of past climate variables because we cannot directly measure past temperatures, so we infer it from other chemical evidences that are related to temperature. That's why we call these as climate proxies. They are a proxy for a climate variable that we are looking for. So let's just look visually at a few of these beautiful things. These are the Speleothems. So you have stalactites and stalagmites from the ground, from the ceiling. They collect a lot of information on climate because the water that is dripping into the caves and creating these beautiful structures is got chemical signatures that can be used to say something about how groundwater, chemistry, rainfall, temperature, etc. were influencing these things. And one of the first things you probably know already is that these things grow at a very, very, very slow time scale, which means the deposition of the information is done at a very slow time scale. So the information you get from these is not very well resolved in time. So we will see that different proxies trap information at different time scales. This becomes very critical as well in inferring past climates. These are the so-called tree rings. So you can see that there are these nice rings that are getting formed, and typically trees form annual rings. Sometimes there is also seasonal information depending on the latitude, the species, the climate variability, and the kind of information that is being trapped or recorded, let's say. So it depends on temperature, rainfall, for example, and the growth bands. Obviously, as the tree grows, the rings keep growing on the outer edge. You can count the number of years if there are annual bands. The thicknesses, you can see the thicknesses are not uniform. If you go from the center to the out, that is related to temperature and precipitation changes. So you need to calibrate these trees to understand the variability of the ring width or distance between rings to some climate variable. So that calibration is a very tricky business as well. We will see that again in a minute. These are ice cores. So this is a 1 meter section of an ice core stored at minus 36 degrees centigrade at the National Ice Core Laboratory in Colorado. What do ice cores have? We will see a little bit more detail. Basically, as snow falls and gets compressed and becomes a glacier, for example on Greenland and Antarctica. The longer the glacier grows, the thicker it gets, the longer the information that is stored in it. So as the snow is getting compressed, it is trapping dust, bubbles, pollen, and so on. So atmospheric composition information, atmospheric gases, various other temperature related informations and so on are recorded in these ice cores, and you have to calibrate from the top to the bottom and see at what time scale the information is being recorded. Amazing science has come, and Richard Alley, the famous glaciologist, paleoclimate person from Penn State University, has a beautiful book called The 2-Mile Time Machine, which tells you how ice cores work. Here is a quick example. So here is the South Pole, and there is various places where ice cores are collected. There are ways to pick the positions of the drilling for ice cores because you want a place that is not on a slope, so it is flowing. You want it on a summit which is recording continuously in time without sliding, and so on and so forth. So there are Dome A, Dome C, Vostok, Sipel Station, Taylor Dome, and so on, where cores get collected, and they give you various lengths of records in time. So you can see how this happens. So if you drill from the top, at the top you still have snow that's recent, so you can see there are gaps in the snow that are getting compressed and trapping bubbles and other material into the ice core. So ice is several hundred to thousands of years old, and there is trapped recent air at the top, and then older and older air. So the ice with air bubbles is preserving information from the past. So as the snow gets compressed, it goes through various stages called hoar, H-O-A-R, and firn. So these are open and porous snow that is already freezing into ice, and so on and so forth. Again, calibration is very critical here. So this is the next part of the same figure. So we are looking at ice cores that have been drilled in different locations in Antarctica using drilling devices like the one depicted here. So in the top center here, air gets trapped in the ice through compaction of snow and firn. These air bubbles in the ice are visible by eye and in the microscope. Sometimes dark ash layers are found in ice cores, which can help to date the ice because they correspond to volcanic eruptions. The dust content changes, which changes the conductivity of the ice. Pure water is not a good conductor, but salts and materials like dust make them more conductive. So the changes in dust amounts can tell you the condition of the climate, whether it was arid, whether it was wet, and so on. And you can imagine that if there is an ice age happening and a lot of glacier growth is happening, then probably the globe is colder, so more dusty, as we will see later on. So here we are looking at bubbles that are visible trapped here with various gases, and so on and so forth. Okay, so this is a sediment core from the Gulf of Mexico at the Center of Marine Environmental Sciences, at the Center for Marine Environmental Sciences at Bremen University. So ocean is producing photosynthesis, biological activity near the surface where there is enough light and nutrients. Those things die and fall to the ground. Of course, other material falls as well. And slowly over time, it gets compacted and more sediment falls on top. So you have sediment cores. Depending on how productive the surface ocean is, we will see that there are regions which are more productive than others for dynamic reasons. So ocean also has deserts and forests, for example, corals, phytoplankton blooms, upwelling regions, downwelling regions, and so on. So the time resolution of the information stored depends on where you are drilling. plus the ocean sediment cores cannot go longer than about 100 million, couple of 100 million years, because the plate tectonics and new ocean floors that keep forming and subducting, etc., basically dismantle the sediments that are older than that. So that kind of puts a time limit on how far you can go back in time using ocean sediments. There are many phytoplankton in the water that form shells, silica shells and calcium carbonate shells. So diatoms, which is this one here, forms a silica shell, and that can fall to the ground and then get buried. So when you take a sediment core, you can get evidence of past climates from it, because the silica shell has signatures in chemistry, magnesium, calcium, silica, other things that are related to temperature at which the shell formed. Okay, so you have to date the diatom to say how old it is, and then you have to infer the temperature from it. That's how you reconstruct the time and temperature change over time. There are a lot of other species corals record as well. We will see a long table which explains all these things. When you want to go longer, you look for geologic sediments and rock formations and outcrops and so on. So here is a limestone outcrop from Mendip Hill, Somerset, UK. This is limestone, so likely formed at the bottom of the ocean, where calcium carbonate forming shells fall to the floor if they don't dissolve along the way, and they get buried into the sediment, and metamorphosis happens over time under pressure and temperature, and then plate tectonics happens and the rock gets outcropped. So you can take information from these that can tell you how old it is, where it was before. So you have to geolocate it in terms of latitude sometimes. You have to time it, date it to say how old it is, and then derive other proxies like temperature and biological productivity and so on and so forth. Of course, we also look at photographic and historically documented evidences like the glacier that we looked at in the last chapter. Argenteuil Glacier in the Swiss Alps or French Alps, for example, provides a good example of how glaciers have retreated. We looked at an example of how glacier has retreated and the glacial lake has formed, and so on and so forth. So documents and photographs help as well. Going back to longer time evidences, these are Foraminifera, again calcium carbonate forming shells that get buried in the sediment. People even count them. So you take the layers of the sediment, you slice it, you date it and say, I am at this year in the past, and then you count the foraminifera in the sediment, and the variability in the number, abundance of foraminifera can give you information about the productivity of the ocean at that time, which means how strong the winds were, how much upwelling and nutrient supply into the light zone, the so-called euphotic zone, was happening. And there are foraminifera that form in the water column, and there are those that live on the bottom. So there are pelagic and benthic foraminifera, that are things that live near the surface, that live below the surface. All kinds of tremendous information exists. So here is an electron microscope picture of fossil foraminifera, so old foraminifera. These are planktic and this is benthic, so you can see they are different. Okay, so where they live depends. And this is pollen locked up in fossils or in ice cores or in sediments and so on. So variability of the sediment, the pollen amount and the composition of the pollen types or species also tells you a lot about past climates. Can you imagine? This is detective work, pure detective work. Okay, so you can see the time resolutions here, 3 rings very closely packed together. So annual, sometimes seasonal bands. Rainy season may record information as opposed to dry season, and so on. Varves are any sediments in the sedimentary rock or the ocean sediments. So those are the layers. You can see this is much sparser than the tree rings. Corals, these are not the same length of time, so you have to be careful. Corals can even give you monthly timescale information when they grow fast about the sea surface temperature, sea level, because they want to grow just close to the surface, above the water, and or just below the water, and so on. And they also record salinity, the rainfall, and so on and so forth. Ice cores, of course, much sparser because accumulation of glacier growth is very slow. We will see something called ice albedo feedback, which makes glaciers grow slower and slower, and we'll see that the melting of the glacier happens much faster. So this is an example of how long tree ring chronologies can be constructed by matching overlapping patterns of different trees. So this is a live tree, this is a dead tree, and this is one that is recovered from long ruins. So it grew at some point, it died, and it got buried in sediment or somewhere that you can dig up and time it, and again look at the tree rings. Gives you a chunk of time in the past when the tree lived and stored the information. Just stunning. So this is again an example of how we get information also from images, historical archives, and other information. So I will leave this here and then come to the idea of isotopes, which are very critical for using the paleoproxies to derive temperatures and sea levels and amounts of monsoon and tree species and so on and so forth. Okay, amazing stuff. So be amazed.